Hello, everybody. This is Professor Ma, and this is the sections on the substitution method for taking antiderivative. We can take derivatives of any elementary functions. So sine x, cosine x, log x, polynomials, multiply or compose them. I can take derivative of it using product rule, quotient rules, and chain rules. Okay. But going backward, taking antiderivative, it's not as simple. In fact, it's not sometimes it's not doable. Okay, for instance, you will not find a functions of like sine x, cosine x, etc., etc. When you take the derivative, you wind up with sine 1 over x. So the antiderivative of sine 1 over x is not a function that I can write down with the traditional formulas. Okay, so that's the first thing to know about antiderivative. That is, not all of them can come out nice and clean. Not doable, simply. Okay. So then how do we approach taking antiderivative? Well, basically the two things we can do. The first things is we can, there's a product rule for taking derivatives. So I can reverse that rule, try to get back to the original formulas. And then there's a chain rule. And I can reverse the chain rule to go back to the original antiderivatives. Okay. So the algebra for in general antiderivative is a lot more complicated. Okay, there are two methods, as I said. Okay, and the methods, this method of substitution and the method of integration by parts in names. Okay, substitution methods reverse the chain rule. And the integration by parts, it's a kind of twisty way unwinding the product rule. We will see the next semesters. And other than that, that's it. These are the rules. So we're going to talk about substitutions. Okay. And the substitution method basically is you reverse the chain rule. When we take a function f of x, okay, where I'm going to write as u, because u actually is a formula in x. For instance, f of x could be log of sine of x, right? And this part will be the u, and then when I take a derivative of this, the x, of course, I'm going to get derivative of log of u. Derivative of log of u is 1 over u, which is sine x. Then have to take the derivative of u prime on top, u prime, which is minus cosine x. Okay, so in this setup, when I see the u, and that its answer will have a u prime in the derivatives, and this gives us a way of observation to go backwards in chain rules. Okay, so in symbols, we have these. So if I take the derivatives of f of u prime, I will get derivative of f times that tail path, u prime. And so when I try to integrate, then what I need to observe is to go backward on chain rule is that when I look at the formula I want to integrate, in the formula, there should be a recognizable formula in x, which is the u, and then next to it, it should have its spin-off, the derivative multiplying to the functions. Okay. So let me list these formulas using the symbols u and u prime. So for example, suppose I'm taking antiderivative of the formula u to some power times u prime, and that's antiderivative, it's going to be u to the p plus 1. For instance, if I'm taking the antiderivatives of, if I take the derivative of sine of x cubed, let's say, okay, then of course I'm going to get 3 times sine x squared times cosine x, right? And so when I take the antiderivatives, and let's just take the antiderivative of sine square of x, cosine x, okay, dx. Let me put a 3 here. Okay, I should get back to that, right? And the problem is, how do I get back to that? Okay, and this is what I meant by u and u prime. So the u is going to be the sine. What? Because the derivative of sine is what? Cosine, and there it is. Its derivative, u prime, multiplying. So this is the form of u squared times u prime. And this enable me to integrate. And how do I integrate? And then this will be changed and back to integrating u squared. And that we will go through that step by step. But first, let me list all the formulas going backwards. Okay. So if I'm integrating sine of something, that's a formula in x, times the derivative, u prime dx. Okay, so in all the following formula, you will recognize the portions. In these trig formulas, you will see that if that's the u you observe, you then need to have its derivative multiplying by dx on the side in the integration formula. If that's the case, then I can apply these substitution methods. Okay, and same thing, if the integrand looks like e to some formula in x, then multiply to it is the derivatives of that formula. Then I can use substitutions, and I can use these to integrate back as exponential formula. Same thing similarly with log. So let me demonstrate, okay? So first we need to recognize that substitution methods should be used, because first we have to recognize that this formula came out of chain rule. So, and the substitution method is a mechanic to, after you recognize that, the mechanics methods will give you back integrations back to the antiderivatives. Okay, so for example, here, let's take a look at it. Here's the integrand, and these, if I were to take the derivative of these, it will give this dx. Okay. If you see that, and that's a key of says, you should go through the substitution methods and call this u, and go through the following steps, and then we can integrate it. Here's how it goes. And here's the step-by-step substitution methods. Okay, so we're going to call that sine of x u. And the next step, we're going to take the derivative of u. Okay, our u prime, of course, is cosine x. And then if I write it, du dx is equal to cosine x, then the same thing I can write. If I solve these in terms of dx, I can write dx as du in terms of formula of u. And the idea is, at this point, we change the entire problems into the variable u. So there's no more problems in x. And that problem in u is going to be a lot simpler, because the derivatives will be canceled out. So what we're going to do, we're going to write the sine of x as the u, that we chose. And then this will become integral of e to the u and cosine x, right? And then we're going to replace dx by these formulas in du. That's du divided by u prime. U prime is the cosine x. And these will cancel out. And this is designed to be canceled out because of dx, that's u prime, the denominator. And we observe u prime is multiplying as a factor. So when I put these two together, okay, that cosine x will, that the u prime will cancel out and leaves us a problem in u. And this is the essence of the algebraic steps. And this is the tricks of called convert the problem from x into a simple problem in u. And this is the substitution methods that this procedure help us to do this. Okay, once we get into problems of u, and we can kind of ignore all these complicated version of problem and integral of eu du. That's of course e to the u, and then the last step is put the u back, put the x back into the position of u. That's e to the sine of x. Okay, so again, the substitution method basically requires, we look at these formulas, okay? We given a problem, we try to match a problem to one of these formulas. Which one? We usually, if you have cosine or cosecant square or cosecant cotangent, usually, the formula can be easily recognized, which one's formula should be used. But the things is important that is you need to have this relationship of be able to spot what the u is supposed to be a formula in x, and as simultaneously the problem should have its derivative multiplying to dx on the side. If that's the case, then I can do the substitution and change the problem to du and the u prime, and this u prime will cancel out. So will leave me a problem in du, in translating entire problem into the letters u. And this is the algebraic tricks. Okay, here's another one. This one's a little harder to see. Where is the u prime? And for this type of problem, fractional one, a lot of time is useful to write the problems with the denominator on the side as a factor, dx. Okay, not cosine x log x, cosine log of x. Okay, so I'm going to write x in the denominator of 1 over x. And if you do that, then you'll say, oh, the derivative of log of x is 1 over x. Therefore, the setting, we're going to set u to be log of x. Then u prime will be 1 over x. And when we do the substitution into u, that 1 over x will automatically cancel with this 1 over x. And so the problem can be then changed into u. So here we go. Log of x is u. So cosine log x is cosine of u. Okay. And dx is going to be replaced. Remember, dx replaced by du over u prime. So we put the u for log, put the dx as du over u prime. So we're going to substitute. Okay, log of x is du. Log of x is u, and derivative of log of x is 1 over x. And so this substitution, the x and 1 over x cancels out, and I wind up with the integrating cosine of u. Of course, this is minus, this is sine of u, and then put the log of x back. Right. So one thing that needs to be mentioned in this problem is another way to sometimes recognize an easy problem is when the substitution is a linear substitution. That is, if the u of x is a linear substitution, then the derivative of u is just going to be a number. It's going to be a constant. It's going to be, like in this case, 3. In this case, linear substitution is always fairly easy to recognize. So let me explain it this way. Okay, let me go down to the following problem. For instance, okay, if I want to integrate e to the minus 5 1/2 x plus 5, and this is a linear terms. Okay, so when it's a linear terms, basically I'm integrating e to the linear terms, and then the integral of this basically is going to be e to the minus 1/2 x plus 5. I'm going to get it back, okay? The entire thing's back. But when I take the derivative of these, I'm going to get e to the minus 1/2 x plus 5. Then I'm going to get, by chain rule, I'm going to get the times the derivative of this minus 1/2 x plus 5. I'm going to get another multiplied by constant minus 1/2. Okay, so the derivative of this is that. But right now, the problem does not have that minus 1/2 in there. So in other words, if I want to take the derivatives to get to my problem, I have to adjust these answers by e to the minus 1/2 x plus 5. I have to multiply these by minus 2. Okay, right, to cancel out the minus 1/2. So when I take the derivative, I will get precisely that. So, in other words, for a lot of time for this linear substitution, I can just take the integral and just take the answers and then adjust the constant to get the final answers. Okay, so and here are some examples you can see. And for instance, over here, antiderivative of cosecant cotan is going to be minus cosecant, right? But it's not exactly minus cosecant of this, because when I use the chain rule, the derivative of just these will have a constant. So what I do is I multiply the reciprocal of that constant to adjust the answers. So some of these problems, when the substitutions u is a linear term, you can just write down the answer, then go backward and take the derivative of it. First you guess what the answer is, then you take the derivative of the answers, and you find out you are all you have to do is adjust by a constant multiply to the answer. And this is the case if the substitution u is a linear terms. Okay, so this is one of the things you can observe. Okay, for instance, this is the integral of a linear terms. Okay, so antiderivative of minus 1/2 is positive 1. So I'm going to start out with, say, the answer is minus 5x plus 3 to the positive 1/2 power. And when I take the derivative of this, okay, I almost get that. I'm going to get minus 5x plus 3 to the minus 1/2. But now 1/2 comes down, right? Now I have to multiply by the derivative inside, which is minus 5. Which means what? Which means this is almost the answer, except there's some extra things over here I don't want. What extra things? These I don't want, because I want the answer only minus 5x plus 3 to the half power. So for this answer, I can take the reciprocal of these. What is that? Minus 2/5 times this minus 5x plus 3 to the 1/2. plus the constants. So when I take a derivative of this and I get this green part, and that reciprocal will cancel that out, and whose derivative is exactly that. So I can kind of guess the answers that adjust by a constant for these linear substitutions. Okay, that's it. This is how we do substitution methods. So, and again, and the trick is to recognize, separate the integrand and recognize these from the chain rule, that is this part of U. You can identify it, and at the same time, and in order for it to work, you have to have the derivative as a factors in the integrand in the problem. Okay, then you go to the substitution procedures. So that's what substitution method is. Okay, and that's it. Bye-bye. Until next time, let's end it.